again, we just expand. So first term. And then remember, the next term then would be something of order eta, but because we're particularly expanding around the classical path, there's nothing there. So it vanishes because it's precisely this statement over here. When you put q equal to the classical path, then that's the first term, but this term precisely vanishes, and then you've got something of order eta squared. And generally, you've got higher powers of eta as well, of course. So that just means all terms of eta squared are higher powers. Now, this thing here, of course, the first term in the exponential, this doesn't depend on eta. So this we just bring out. This is just an overall factor. And so integral of e to the I over h bar, and then something stuff of order eta squared. So let me just loosely call that thing, whatever it happens to be, some new action that depends on eta, so S tilde of eta. And again, just to remind you, of course, the classical path always obeyed the condition that it started at the initial point and ended at the final point. And so if we take paths of the form q classical plus eta, then eta has to vanish. So eta of 0 is eta of capital T, which is 0. Okay, so this thing here is a path integral where you're integrating over eta, but always subject to the condition that eta starts at the origin and ends up at the origin. But so it's just a special case of what we've been doing. And of course, you can work out what this action is from the action you started with just by doing this expansion. Now, in general, of course, this expansion, these terms here, involve details of this classical path. And this thing here, we can't, I mean, apart from the fact that the endpoints are special, they're chosen to the origin in this case, there's no reason why we should expect that we necessarily do this path integral. However, special case is when the original action was just quadratic, then this new action here turns out to be, again, just quadratic, but also completely independent of the classical path. So this is a special case. We have a quadratic Lagrangian. So let's just, just to be complete, let's just write down what we mean and see how this happens. So you can have a term A times Q squared, that's obviously quadratic, B times Q dot, C times Q dot squared. So these are all quadratic. And then you can have terms plus linear plus constant if you want. So these A, B's, and C's here are just constants. So if we extended this to allow time-dependent Lagrangians, which we can easily do, then A, B, and C can be functions of time. So if we have that, then L of Q classical plus eta Q classical dot plus eta dot So again, just doing Taylor expansion, of course, this is L of Q classical dot. And then generally you would get terms that were linear in eta, but precisely because of our equations of motion, because we're using expansion around the classical path, again, the Euler-Lagrange equations mean these linear terms precisely vanish. So there's no terms linear in eta, so these order of eta terms, this goes to 0. By the Euler-Lagrange equation, because we're expanding around the classical path. Okay, so this term, it's clear this just simply vanishes. And then the next term you can get must be of order eta squared. And of course, well, you can either write it all out explicitly, or you can just see the only way you can get terms that have got two etas in them, of course, is from when you expand these things, putting in q, this q classical plus eta. And so what you get there, well, you can get an eta squared out of that, so a times eta squared. And then you can get b eta dot plus c eta dot squared. And then that's all, because you can't get eta cubed out of this because it's at most quadratic in the q to start with. So that's exactly what you have. You get the classical action plus this thing here. So you see that this is, of course, exactly the same as the classical action, except you've removed all the linear and the constant terms. It's even slightly simpler than the classical action. Okay, so So let's call this thing here L tilde of eta dot. Okay, so you can easily see, of course, if I started with something more complicated where I had higher powers of q in my original Lagrangian, then I still get terms in here that involve the classical path, and I've got higher powers of eta in here. So this is a very simple case where absolutely no dependence on the classical path even appears in what this Lagrangian is. It's just exactly what you started with, removing all linear and constant terms. So if we go back here, then our original path integral, which was this overall factor involving the classical action, and then times this path integral here. Well, this thing here, this S tilde, is just the action we got from that L tilde, the Lagrangian I wrote down there. It only depends on eta and is quadratic. But it's got no dependence at all on the classical path, so it knows nothing about the initial and final points that we had for our q. And so the only thing it can depend on then, of course, is the time interval t. So S tilde is just the integral of this L tilde over time. So it only depends on the time interval. Okay, so if you had time dependence explicitly in the Lagrangian, it could depend, of course, explicitly on the initial and the final time. But it doesn't even depend on the initial and final position of the particle, because eta is just a variation. Eta at time 0 is 0, and eta at time capital T is 0. So there's no dependence whatsoever on the classical path here, or the initial and final position. So this is just some overall factor, which is just... So basically this is something, it's just some function of t. So the result here is then for a path integral is some function of t, which comes from this here. We just call that f of t, and then e to the I over h bar is the classical, well, s of q classical. So if you don't care about this function of t out here, in fact, then that's all the information is really in the classical part here. So you just have to work out what the classical solution is for a particle starting at qi, finishing at qf, moving for time t, and put it back in the action, evaluate that, and that thing here is your path integral up to this over L function of t. Okay, so how are we doing? Okay. Right. So okay, so let's do the simplest example we can. So simplest example is when we just do a free particle with no potential at all. Okay, so this will be a case where, of course, the Lagrangian will be quadratic, but if we've got no potential at all, then all this stuff vanishes. These things aren't there. So it's just going to be a kinetic term in the Lagrangian. So what we'll do, actually, we'll just explicitly evaluate the path integral using this here, just to show you that you can do it in these sort of cases. And then we'll see that the result at the end does agree with this, of course, as it has to do. And if we explicitly evaluate it, we get precisely this function of t here at the same time. Okay, so let me first ask, is there any questions anyone's got about what we're doing so far? No? Yeah.
Is constant here?
Sorry?
Q classic.
Yeah.
The classical path.
Yeah, the classical path, yes.
Constant, not variable?
No, so we have what we're solving here, remember, so we're solving a particle that starts at some position, so qi at, say, time equals 0, and it finishes up here at qf at time equals capital T. Okay, so, and the path then takes some classical path. So this is just solving classical equations of motion. And then we have this path. Now, essentially, what you have, of course, your classical equations of motion are second-order equations. And so we've got one piece of initial data here, one piece of final data here. So we've specified, roughly speaking, we've specified enough data then to fix the two integration constants you get when solving the classical equations of motion. So, if, for example, this is, so let's take, so the general case, the Lagrangian then, so it's a kinetic energy, so half mq dot squared, and then you have some potential v of q. Okay, and then, so dl by dq is just, so that's depending on q dot, this is depending on q, so this is minus dv by dq. And dl by dq dot, you get just the term from here, which is m q dot, which is the momentum. And so this equation, or the Lagrange equation up here, which I just removed,